All right, so this is a talk. These slides are from our talk at Plumbers last September. When we gave the talk at Plumbers, it was actually a joint talk between me and Carlos. So Carlos is the, the person who does most of the development on the C implementation of the binder driver. So I'm going to be giving his part today as well, but you can imagine that it was given by the guy who does the C driver. So, the binder driver, what is that? So this is some, it's a driver on Android. It's actually upstream, it's in driver/Android. And it's used for cross-process communication. So you have two processes on your phone. They want to talk to each other. And then they just they send a message to a binder, and they send a reply, and that's what binder does. So it's an alternative to pipes or dbus or sockets or whatever to talk between processes. Yeah, I mean, yet another IPC. It's it's been used on Android. It originated a long time ago in some other mobile operating systems. But the thing to understand is that although binder is pretty rare outside of Android, it's used very extensively in Android. Almost all processes on an Android phone are going to be using binder to some extent to talk to other stuff. For example, like anytime you want to talk to the Android framework from an app or whatever, that probably goes over binder. It's composed of libbinder, which is a user space library written in C++, and the binder driver in the kernel. So the idea is this kind of client-server model. We have some sort of service. You have clients that want to send messages, and so there's this memory map region in the servers in the services memory space. And then when I want to send a message, I just copy it into the memory map region. Well, the kernel does that for us. And then the service has a thread pool, and then binder will assign the incoming message to one of these threads and wake it up and do all of that nice stuff. So that's kind of the idea. So why have this binder driver instead of pipes? I mean, so it provides actually a lot of features that other things don't have, or some of them have them. So there's also sorts of stuff like there's no buffering in the kernel, so you copy directly from the user space of one process into the user space of another process. So that's very nice for performance reasons. That's write and read in a single octal. It can even do priority inheritance because it knows that this thread of this service is handling a request from this high priority client. So because the kernel has knowledge of this client-server relationship, it can do these kind of priority inheritance. And lots of other stuff. File descriptors, reference counting of objects cross processes. It's all very interesting. But yeah. There have been some attempts to replace binder with something else, but it's actually really difficult to beat binder latency-wise. And part of this has to do with this thing with that the kernel actually knows about the relationship between the client and server. It can use this to do, well, for example, priority inheritance, which is not so easy to do with pipes. So, why are we rewriting the binder driver? So, the binder driver faces some challenges. Over time, it's really a high complexity driver. There's a lot of, I mean, you saw it on the previous slide. It has a lot of features, actually. It's not just copy the data. It does a lot of other stuff. So and that's the essential complexity. But the other thing is, it has accumulated a lot of technical debt. Should we call it perhaps? Just craft that. That's very natural as a code base evolves. Like that's just how it is. But the binary driver could use some reduction of that. But the thing is, the binary driver also has security issues. And the challenge is that because it's so complicated, it's really difficult to simplify the driver without introducing a security vulnerability as part of that. And so binder is a very security critical part of the kernel, at least on Android. The vulnerability density is very high. It's 3.1 vulnerabilities per 1,000 lines of code, which is one of the highest in all of Android. The other thing is that, it's not getting better. We have around 3 per year, and we've done so for that for many years in a row. Now the thing is, there are a lot of, vulnerabilities out there that don't really matter because nobody uses them for any exploit. But that's not the case in binder. Binder vulnerabilities are regularly exploited to cause harm. We know of exploits for about half of the vulnerabilities in binder. And part of the reason for that is that it's security critical, right? Anytime you have some sort of thing that's, for example, sandboxed, well, the sandbox still needs to talk to the outside world, and the way that happens is over binder. Yeah. It has high complexity, a lot of complex features, and it's really important that we not only implement these features correctly, but also that we do it quickly with low latency, fast and efficient. And minor performance regressions can noticeably cause your user interface on your phone to be Yankee. So it's really important that we implement these high complex things, what's it called? Quickly. So this is an example of the tech debt. This is one function. With all of the line breaks removed. So we have long functions, we have lots of error handling. This is about 1/3 of the error handling in one of the functions. Now the thing is, improving the code is actually risky. Right? And this is a problem because we have had bug fixes that have introduced. Actually, so we had a simple refactoring in the kernel. It introduced a vulnerability. You can see the fix here on the screen. It was a asterisk that should have been a slash. But the thing is, this turned into a real vulnerability, and this is not like a unique example either. Like we have had, bug fixes that introduced vulnerabilities. We've had fixes for vulnerabilities that introduced vulnerabilities. We've had chains where we fixed a vulnerability and the fix for that vulnerability introduced another vulnerability. Okay, so that's the end of Carlos's part of the talk. Now it's my turn. So, Rust binder, that's what I work on. Yeah, we have the Android over here, then we have the Rust mascot, and you can see a happy Rust Android, yeah. So, we're rewriting it, but why do it in Rust? So, one of the things that I think is really important is this ability. Right, so Rust has many different types of pointers that are, encode what is the specific way we're using this pointer in? Right? For example, here you have a function which takes a reference count that points to something, but it doesn't take ownership of the reference count. That's what I can read in the signature. And if the caller doesn't follow that contract, it's not going to compile. In the C driver, we don't have that kind of check for us. Like, you have to do it yourself. You can have this kind of check, of course, but that's not at compile time.
And if you want to do it at compile time, it will be macro.
That's not so easy. Another example of the same thing, when you have structs, we have a lot of pointers in these structs. In Rust, because we have different pointer types depending on how the pointer is used, we can encode the ownership in the declaration of the struct. So here we have, for example, the box here, that means exclusive ownership. Then there's an arc around the thread, that means atomic reference count. So that's a pointer to thread that owns a reference count. And then there's an option arc. That's like an arc, except it's nullable, so it might be null. And these are approximately the same ownership semantics you have in the C driver. But you just have to hope that the developer actually wrote down in some comment and if they didn't, well, now you have to go check the code. Maybe you have to go check the code anyway in case it's wrong or outdated. Here's another example. I'm not going to comment further on this. The other thing is, I mentioned that Rust has a history of having a lot of vulnerabilities. And if you actually go in and look at the list and categorize them, you will find that the vast majority of them are things that Rust would have caught or would have prevented. Or, in some cases, for example, out of bounds, Rust doesn't catch that at compile time, but it's still going to turn into, for example, a panic, which, at least from our perspective, turns a high severity security vulnerability into just a denial of service, which of course is bad, but it's much less severe. And so, it either prevents at compile time or at least makes them much less severe in almost all of the vulnerabilities. And I think that's really why the security team wants this. So, Rust binder. I have it right here. You can see there's Rust inside. This little sticker. So it's at feature parity. It's really not only does it pass test, you have to remember this is half a year old. Today I use this as my daily driver. This is the only phone I use. It's good enough for that. I don't run into any particular problems, so that's pretty awesome. Now the other thing is, I talked a bunch about security and so on, but we shouldn't forget performance. We have some benchmarks. We're working on new ones, right? We're on the kernel version, everything has changed, but it's pretty good. I would say that at this point we were pretty much at par, and I think we probably also are pretty much at par today. So you have to remember the C driver, it's a fast driver. It's not some serious optimization work has gone into the C driver and also the Rust driver. But it's a hard contender. There's also the code size. And, it's kind of, in Rust, it might be more verbose when you have to, declare more information in the type system, like, oh, this pointer is like this. So you don't just say it's a pointer. So maybe you spend more lines of code on that, but then Maybe you spend less code of error handling. This is the numbers we got, so basically the same. So yeah. Now, what about unsafe? This is a big talking point when it comes to Rust. Now, the deal with binder is that we actually didn't write the entire driver in Rust. There's a file system called binder.fs, and we just kept the C implementation because it doesn't have a history of security vulnerabilities, and converting it would have been a lot of work. So yeah, so most of the unsafe Rust in the binder driver itself has to do with talking to this C component. There are also some other minor stuff, but even then, 4% is not that much. Now, of course, there's also this thing called an abstraction or binding. So this is, for example, the work queue or the linked list, right? So this is, let's say, a Rust library that wraps some underlying C interface in most of the cases, right? And so if we take the work queue, the thing is there's unsafe code in the work queue. But the thing that Rust is really good at, and that I think is one of the most important parts about Rust, is that you can encapsulate unsafe. The work queue API that you can use from Rust, as far as we know, there's no way to misuse that API to cause memory safety. Of course, there can be bugs, right? But the intent is that the work queue API should be designed such that even though there's unsafe inside it, users of the work queue should not be able to do something weird that causes that unsafe code to misbehave. And so we can kind of encapsulate this unsafe, and if we just get the work queue right once, the work queue wrapper abstraction, then all drivers will suddenly have access to the work queue and not have to worry about memory and safety. That's kind of the idea. So, at some point, I was telling Ricardo that I work with, well, in my office, that about like all of the stuff that binder driver does, and this is what he had to say.
Get started. Patrick, so welcome. When will it be in the mainline consumer Android? 14?
Well, we're not supposed to make forward-looking statements. But, we're hoping to do some testing on phones, and if it behaves well, hopefully it will go upstream and delete the C driver.
So I was wondering about the abstractions. Were there any challenges in writing the abstractions?
Whether there are challenges?
Like, I mean, is it just like mechanical implementation of interfaces, or is there
No,
some?
it's not mechanical. I think that for some abstractions it's going to be relatively easy, but some of them, it actually turns out that figuring out how to express the requirements for using the C interface is pretty tricky, because first you have to understand what are the requirements for the C interface, right? For example, I've been wrapping the struct file API, and it turns out it has some really complex reference counting. And so, we had to spend, I had to first talk with C maintainers, figure out how does this actually work. And I actually misunderstood some things, and the earlier versions of the patch set were wrong, right? But then I figured it out, and then I found a way to encode that in the Rust abstractions, right? So that's to say it's not mechanical, right?
Thank you.
It's perhaps worth mentioning that you have the bindings, which are automatically generated from header files and are just exactly the C functions. That's not what I'm talking about. I'm talking about nice to use, well-designed, safe Rust APIs that are built on top of that.
Yeah, thank you.
Question down here. Hand up again.
Oh, there's a question.
Hello. Do you have any mechanism in place? So let's say you make an abstraction for work use and you make an assumption and you specify that contract. That API has a contract and you make that contract in Rust. Do you have some flags or something in C to say, hey, if you change this assumption, fix this in the Rust part, or you don't have anything like that?
Well, I mean, so if you change the signature of one of the functions, of course, Rust is going to notice because we have automatically generated things from the header files, and that's going to change, and then it's not going to compile. But if it's something about the semantics, well, I mean, Rust only has the interface of the C code to go by. And so the best you can do is to add a comment in the C code to say, if you change this, you also need to change Rust.
And we have something like that today in...
Well, I mean, we have comments. Thank you.
Reuse testing.
I would say the same goes for any use of that function.
Yeah, that's true. You have to check all users, including Rust.
Yes, I got a question. So what type of vulnerabilities do you foresee? What would be the weakness in Rust here?
So we actually have had somebody discover vulnerability in the Rust binder driver.
Oh.
Now, the interesting thing is, it's not one of the vulnerabilities that Rust promises to prevent.
No, but that's not like
Exactly.
what should you watch out for? Like Rust is not something that solves everything, right? So
Right. So the vulnerability was essentially some sort of logic error where the internal data structures got confused about what was there, and then it, incremented some integers the wrong amount, and then this caused the driver to send invalid data to another process, and then you could, cause use after freeze in that other process, right? So there was no memory and safety in the kernel, which is what Rust promises to prevent. But still, it's probably not so good if you can cause memory and safety in system server, right? But I think it's interesting because the thing is, CBinder had almost the same vulnerability. And when CBinder had what was basically the same vulnerability, then it was also memory unsafe in the kernel. So you could trigger use after free in the kernel. And so when the same thing happened in Rust, the use after free was not there, but the logic error remained.
So that means you had one vulnerability per 50K lock or something like that. 5.5.
I guess so.
Yeah.
yeah, are all the Google guys working on Binder, have they all converted to Rust, or is like, I mean, do you need to have people who gonna continue and build on Rust, and you like rewrote it, but are they gonna like, will it be the same group of people, or it's a new bunch of Rust converts going into this, or can you answer?
Ultimately we'll have to see, right?
Yeah.
But so the maintainer who's going to eventually take Rust binder into upstream is Greg KH, and he has a very strict policy called no duplicate drivers. So to convince him to merge it, we have to make it good enough to replace the C driver. At that point, well, now the C driver's gone.
Yeah.
So how is that going to work as a maintenance process if you replace the binders driver from C to Rust, if you find, like, for example, the vulnerability you discovered, that would be normally something you fix, and you also CC stable for all the versions to be fixed as well. But now C is gone, you fix Rust. So you have double the work to do because you have to go back to the C and see and check if that same problem is there as well for the backporting. So because it's Android, I don't know if you care as much about fixing LTS behind mainline.
Oh, we do care about that
but-
because most of the phones are on old stuff.
So you never fix anything, or
No, we submit fixes.
so you will have going forward kind of until
Yeah, there will
all
be
the
there will
C-
be some, the C driver, just because we delete it in mainline doesn't mean it's going to go away for many years.
Okay, so you are ready for all that overhead.
Yeah, we know about that. That's not going to be a surprise when that comes.
Okay.
That's just how it is.
So I guess this is more of a generic Rust in the kernel question, but you mentioned panicking on out of bounds. And I know Linus has been very negative to that approach. Do you know the current status of Rust in that regard, avoiding panics?
I mean, if you're doing out of bounds of an array, what do you want us to do?
Yeah, I don't know, but no, but I'm not.
So the current
yeah.
status is that if you do an out of bounds on a Rust array, you're going to cause a panic.
Okay. Yep.
Yeah, I mean, if you do an out of bounds in the kernel, then either you have a seg fault, which is, I guess, similar to a panic in effect, or you have a security vulnerability, which, well, you probably have both.